So I'm going to start with the recursive cases. So the base cases will go here. So we'll come to those in a few slides. All right, so to start with, I want to know, well, what's the square I'm standing on right now? Because I need to know how many squares left or right I want to go. So I ask the board, what is your value at that index? Right? Now remember, with the list, the method get returns an element from the list, right? Given an index. Okay, so I'm on this square at position index. Right? I want some way to remember that I've stepped on this square before. So what I'm going to do, oh wait, let's go back one step here. Notice that the contract or the documentation for this method says that the method does not modify the board. Right? What it really should say is that it does not permanently modify the board. So when you call the method, right, when the method is finished, that board is the same board that was passed in originally to the method. Right? And that's nice because you don't want a method that changes the values of the board, right? Because then whoever called the method, they now have a modified board. You don't want that. All right, so I'm going to go ahead and change the board anyway. Right? So I'm going to call set, and I'm going to replace the current value in the board with the value -1. Right? Now remember, all the values in the board are supposed to be positive, except for the last one, which is 0. Right? So I'm going to use -1, a negative value, to indicate that we've been on this square before. Right? And so we'll come back to how we use that in the base cases. Right? Now you might say, well, you're changing the board and the method says it doesn't change the board. That's fine. You just have to unset the square when you're done with it. Right? So we'll unset this. We'll put it back to its original value later. And that's why I remember it up here. Okay, next step. I want to determine, can I move left? Right? If you're on that current square, right, and that's the value of the square, then the index of the square to the left is just index minus value. Right? That has to be an index, so it's valid as long as it's greater than or equal to 0. So if that value is greater than or equal to 0, I can move left. So I'm just going to try moving left. Right? So I'm going to call is solvable. Right? I'm going to pass in index minus value, because that's the location of the square after moving to the left. And I'm going to pass in the current board. Right? Now notice when you pass in the board, right, the next version of the method gets the board that has a -1 sitting in it somewhere. Right? And so the next version of the method gets to know, hey, you've already been on this square before. Right? So this method runs, it does its work, right? And eventually it returns true or false. Right? You then want to test whether or not you can win by going right. So the index of the square to the right, starting from that index there, right, starting from that position there, is just index plus value. Right? That's a valid index as long as it's less than the size of the board. So if that value is less than the size of the board, we can move right. Right? After moving right, you want to test, is the board solvable? So you just call is solvable again. Right? Again, right, this version of is solvable gets a version of the board that's got a -1 sitting somewhere on it. Right? Okay, so is solvable runs, right, does its stuff, and eventually returns true or false. Right? And so now I know, can you win by moving left, and can you win by moving right? If either one of those is true, right, we can go ahead and return that value. Right? What we actually want to do is we want to return the value of win left. Oops, sorry. We want to return the value of win left or win right. Right? If either one of these is true, we want to return true. If they're both false, we want to return false. Right? And so the value that we want to return is just the or of those two values. Now remember, we can't modify the board, or we can't permanently modify the board. So before I return a value, I have to unset the value at position index. Right? I have to restore it to its original value. Now, when you call the method recursively, right, that version of is solvable is going to mark another square on the board. Right? So here we've marked one position on the board. we call is solvable again, it's going to mark a second position on the board, right? If it calls is solvable again, that one's going to mark a third position, and so on, and so on, and so on, right? As each version of the method returns, though, it unsets a position on the board, right? So set one position here. That version is going to set a second version. When it returns, it's going to unset the second square, right? And now when this version of the method returns, it's going to unset the square that it set at the beginning. So this restores the state of the board, right? And there's one version of your recursive cases, right? Any questions about what just happened there? Anybody? All right, moving right along. What about the base case? Sorry. Do you have a question about what's going on here?
Oh, yeah. In the what is a copy later passing over is solvable?
Oh, I'm sorry. This is an edited version of the slide. There was an old version of the slide where I actually made an explicit copy of the board. That should just be board. Thank you. Yeah. So you're just going to pass in the board. There's an old version of this slide where I copied the board every time. So if you copy the board, you don't care. You're never worried about whether or not you modify the copy, right? You don't have to do the copy, right? It's sufficient to set and then unset the board in each version inside the method. Right? I guess one of the confusing parts about this method is if you're not comfortable with recursion, or if you don't actually understand what happens during recursion, is that when you call is solvable again, it's going to change another square on the board, right? And it doesn't, if you're unclear about how recursion actually works, right, you might think, well, I'm only unsetting one square on the board. What about all the squares that this one caused to be set, right? And so the answer is that as this method returns, right, it unsets the square that it set, right? And so this really does leave the board unmodified. Any other questions? Yes?
Can you just explain again why you made one last false?
Oh, here. I have to initialize it to something, right? So you don't, sorry, technically that's not true. I could have just written Boolean when left and left it unset, right? And when you call is solvable, oh, actually that's not true. You have to set it here. If you don't set it here, right, that if statement, the condition here might be false, right? If the condition's false, we never set when left, right? And so in Java, that results in a variable when left that's never initialized, and the compiler will complain. Yeah, you're welcome. Any other questions? All right. What about the base cases, right? And so for the base cases, you have to remember there's a situation where we know the answer must be false, right? So one of those cases is when you hit a cycle, right? How do you know that you've hit a cycle? When you land on a square whose value got set to -1, right? Because that indicates you've landed on a square that you've seen before. So that, whoops, sorry, that's going to be one of our base cases, right? That's the one that returns false, right? Now, this is a method that returns a Boolean value, right? So it returns true or false. Often in these recursive methods, if there's a base, if it returns a Boolean, there's a base case that corresponds to both true and false, right? So there's our false one, right? You land on a square whose value is -1, the board is not solvable, right? There is an obvious case where you return true, right? You return true if you land on the last square of the board, right? And so there's your second base case. So those are easy, right? If the value that you land on is less than 0, you found a cycle. I want to abandon that solution, so I'm going to return false, right? If the location of the square that you land on is the last location in the list, right? You've reached the end of the board, so you're going to return true, right? And now the rest of your method goes here, right? The recursive cases deal with moving left and right. Your base cases determine whether or not your method can terminate. All right, any questions about the base cases? Right, now, when you write these recursive methods, it's tempting to write extra base cases, right? So you might be able to cook up a situation where if there's 2 squares on the board, right, maybe there is or isn't a solution, right? you don't have to write those base cases, right? Because those base cases will be handled by the recursive cases. It's not incorrect if you add in extra base cases, but you have to make sure that these two base cases are covered. Right? If you're missing either one of these, the method will either never complete or it will return an incorrect value. All right, any questions on that, solving that problem there? Right. Again, it's not at all clear if you can solve this particular problem using a loop somehow, or loops, right, perhaps nested. The problem in these types of the problem in this particular case is that if you were to try to write a loop, right, each time through the loop you have to consider what happens in two separate cases, right? For each one of those two separate cases, you have to consider what happens in two more separate cases, right? Can I move left? Can I move right? Right? And so you end up with an exponential number of branches that you have to consider. Right? These kinds of problems, so if you studied binary trees, right? In a binary tree, you've got two choices at every node, right? Often, many of the binary tree methods, you're often taught those recursively, right? It's simply easier to write them recursively than it is to write them iteratively. All right, one more recursive method, I think. All right, so this one's going to use sublist again. So I'm going to start by describing a simple problem, and then I'm going to use that to build a sorting method. So what I'm going to do is I want to solve the problem of searching a list for the smallest value in the list. When I find that smallest value, I'd like to move it to the front of the list. Right, now this one you can easily write iteratively. Right? Write a loop, find the smallest element in the list. Right? When you found the smallest element, so when you've searched all the elements in the list, take the smallest element, swap it with the first element in the list. Right? That solves the problem. I claim you can do this recursively. Right? So here's the idea. There's my original list. Right? So it contains the numbers 0 through 9. I would like to move the smallest element in that list, so the 0. I would like to move it to the front of the list, right? Possibly rearranging all of the other elements in the list, right? I don't care what happens. Like, I don't care how the rearrangement happens, right? I don't want to remove elements from the list. I don't want to change values that are in the list, right? I just want to rearrange them. So here's the idea, right? Suppose I can find the, so I'm going to ignore the first element, right? Ignore the 8. What happens if I move the smallest element in that sublist, shown in blue, to the front of the list? Right? Well, the 0 comes to the front of the blue list. Right? Something happens to all of the other elements. I don't care. Right? They're rearranged somehow. You don't exactly care what happens. Right? So what's the situation now? Well, I've got the 8 sitting here, right? The original first value. I have the smallest value in the blue list sitting here. What's the smallest value in the list? Well, it's either the 8 or the 0. Right? It's the one that I ignored at the beginning, right? Or it's the smallest element in the rest of the list. So I just compare them. Right? If the element at the front of the blue list is smaller, I just switch these two elements. Right? And now the smallest element is at the front of the list. Right? And so that's your recursive method. Right? Recursively find the smallest element in the rest of the list. Compare the first two elements in the lists. Swap them if necessary. Right? And so there's the recursive version of min to front. Right? So ignore the base case. Right? First step, recursively find the smallest element in the list, not including the first element. Right? So the smallest element in the rest of the list I can find recursively by using min to front. Right? Now, what list do I want to pass in? Well, I want to pass in the list that does not include the first element of the list. So I can use sublist for that. Right? So sublist returns the part of t, right? Starting at index 1, going up to but not including t dot size, the element at t dot size. So going up to element t size minus 1, which is the last element of the list. Right? So that recursively finds the smallest element in the list, excluding the first element. And now I do the comparison here. Right? The first element in the list, you get by calling get, so t get 0. The second element in the list you get by calling get, so it's tget1. If the second element is less than the first element, switch the first and second, right? So how do you set an element in the list? Well, you call set, right? So I'm going to set the element in index 0 to second. I'm going to set the element in index 1 to first, right? And that's the recursive part of the method. How do I know I'm done? Right? So that recursive step finds the smallest element in the rest of the list, not including the first element. Right? It recursively calls itself, so it finds the smallest element, not including the first two elements in the list. Right? It recursively calls itself, it finds the smallest element, not including the first three elements, and so on and so on and so on. Right? Eventually, you reach a list whose size is either 1 or 0, depending on where you started from. Right? So if you have a list of size 0, right, there's nothing to do. There is no smallest element. Right? If you have a list of size 1, there's nothing to do. The smallest element is already at the front of the list. So if the size of the list is less than 2, you're done. Right? You can simply return. There's nothing to do. Right? And that recursively moves the smallest element in a list to the front of the list. Right? Again, you can easily do this with a loop. Right? But you can also do this using recursion. All right, so what happens if you repeat this process? Right, so I've moved the smallest element of the list to the front. So the 0 is now sitting here. Right? Something happened to these elements here. I don't exactly care what happened. Right? Let's say you get that. Right? Now what happens if I call min to front again on the blue list? Right? Well, that's going to move the 1 to the front. Right? So that moves the 1 to the front of the list, and we get 0 and 1. Right? Now, what if we do that again? So I recursively call min to front on the rest of the list. Right? Well, that moves the 2 to the front of the list. Right? And now I've got the 0 and the 1 and the 2. And if I keep on going, right, you end up with a sorted list. Right? And that's exactly the selection sort algorithm, which I don't know if they taught you or not. Right? If you've done any sorting, you may have seen selection sort. So it's one of the quote-unquote simple sorting algorithms. It runs in O(n) squared time. Right? So it's not one of the quote-unquote efficient comparison sorting algorithms, right? But it's one of the simple ones to implement. How simple is it? It's that simple. Right? Assuming you have min to front, right, you just call min to front. Right? And then you recursively call selection sort, passing in the rest of the list to sort. Right? So that moves the smallest element to the front. Right? Now recursively move the smallest element in the rest of the list to the front of the rest of the list. Right? And keep on going until you sorted the list. Right? How do you know you're done? Right? So if the size of the list is ever 1 or 0, you're done. Right? And so another way to write that, instead of putting in an explicit base case, right, I can simply say, if the size of the list is greater than 1, recursively sort the list. Right? Eventually, the sublist reaches a size of 1 or 0, and the method stops. Right? And so selection sort becomes 3 lines, assuming you have min to front implemented already. Right? And so that's how selection sort works. Often when students are taught selection sort, they're shown the iterative version of the method. Right? But if you just look at the iterative version of the method, it's not really clear what's going on in that method. Here, it's obvious. I'm going to move the smallest element to the front, and then I'm going to sort the rest of the list. Right? And so there's another example of recursion on a list, right? Again, using a sublist to help us do the recursion. All right, any questions about that? Okay, so it's unclear to me how they taught you computational complexity, right? If you were to analyze the complexity of this algorithm, right, the quote-unquote correct way to do it is to write down what's called the recurrence relation for the algorithm. Right? So I'm going to cook up this function called t. Right? The function is just the number of operations needed to sort a list of size n. Right? And so when you look at the recursive version of selection sort, right, you ask yourself, well, what does it do? Right? So t of n is going to be the number of operations needed to sort the list. Right? So what does this do at each step? Well, it selection sorts a list that's one smaller than the previous list, right? So to sort a list of size n, you need to sort a list of size n minus 1, right? What else do you have to do? Well, I need this min to front step, right? So I need to move the smallest element to the front of this list, right? So if you think about how you would do this iteratively, you'd write a loop that looks at all n elements of the list, and then you would swap the first and smallest element, right? And so that step there, you know, takes something that's proportional to n steps, right? So we say that takes big O of n time, right? You can solve that recurrence relation for n. You can solve that recurrence relation and show that that's in O n squared complexity, right? Whether or not you were taught how to do this in your previous courses is not important here, right? The important part here is that this particular algorithm is in O n squared, right? If they taught you any sorting algorithms, you were probably taught merge sort or quick sort, and you know that those are in O n log n, right? So much faster than selection sort, right? Okay, good morning, everybody. So today is the first lecture where we start to actually talk about the object-oriented part of Java. So we're going to start implementing our own classes now, where you're using the classes to actually make objects. So far, you've implemented some classes, but you haven't been making objects using those classes. So to begin, I'm just going to quickly review some fundamental terms to make sure everybody's clear on these terms when I talk about them. All right, so remember what a type is. So a type is just a set of values and the operations that you can perform with those values. Right? So for example, an int, it's just the integer values between integer min value and integer max value. So those are your set of values. Right? What can you do with an int? Well, you can do arithmetic with an int. Right? Similarly, you've got your reference types. So you've got something like string. A string is any sequence of 0 or more characters. So there are your set of values. What can you do with a string? Well, we saw strings had some methods like index of, char at, substring, and so on and so on and so forth. Right? So a class is just a user-defined type, or is a user-defined type. And similarly with list. Right? So Java's got your primitive types, and Java has reference types. Right? So your primitive types are the types that are, quote, built in. Right? So any type that begins with a lowercase letter, you know is a primitive type. Right? So they represent the numeric types in Java, and they represent the type true, false. Finally, you've got your reference types. So anything that's not primitive is a reference type. And that means arrays are also of reference type, right? Even though they don't necessarily look like that. So if you make an array of int, right, the elements inside the array are primitive, but the array itself is a reference type, is actually an object, right? So it's a reference type. Right, and we've seen string, we've seen array list, and sets and maps already. So classes are just implementations of a reference type, right? So they're user-defined types. So in Java, a class is a type. There are types also that are not classes, right? So there are things called interfaces as well that are also types. Right? So array list is a type, string is a type. They're both classes. This thing called list is not a type, is a type, but it's not a class, right? So it's something called an interface. And finally, objects are just instances of a class, right? So like the number 5 is an instance of an int, right? If you make an array list object by writing new array list, by calling the array list constructor, you end up with an instance of an array list. So the one way to think about objects is that an object is just a copy of a class, right? So you use the class to make, as a blueprint, to stamp out or to produce objects, right? So when you make an object, you can think about, one way to think about it is like you're making a copy of a class, and you're using that copy to, as your object. All right, so these things called reference types, they're called that because a reference type variable stores a reference, right? So a reference is just something that lets you identify a particular object. So in Java, most implementations, references are memory addresses. So they're like pointers. Any variable whose type, right? So we said that t is a reference. Right, so here, that variable t, because t is a reference type, right? So t stores a reference to an array list object in this particular case, right? For C programmers, you can think of it as t is a pointer to an array list object, right? It lets you find that object in memory. All right, so to make this clear, you can sketch out what's called a memory diagram. So a memory diagram is it's just a table. Right? It's got 3 columns, right? And it's supposed to be a picture of what's in memory. And so in our right-hand column, we've got something called the value. Right? So that's the actual value that's stored in memory on your computer. Right? When you store a value here, you're only allowed to store one thing in each square. Right? So I can put one thing there, I can put one thing there, I can put one thing there, and so on and so on and so on. For our purposes, it will always be a number. Right? So after all, in your computer, everything's just bits, right? So just ones and zeros. So we can just interpret these values as numbers. The middle column is going to be the address. So I'm just going to label the blocks or the square or the rectangles, I guess, from 0 up. So you can think of the address as just being an index, right? So if you imagine that this is an array, that's the index into that particular array element. And finally, we want to sketch out memory, so we have variables in memory. So the first column is if we have a variable and it has a name, we'll put the name in the first column. And so the difference between a primitive type and a reference type is shown in this picture here. Right, so imagine you have a little program. It makes a variable x, whose type is double. So in memory somewhere, that thing x has to be stored. Right? You can put this wherever you want. It doesn't have to be where I'm showing you right now. Right? So you just pick one of these rows, and you label it with x. Right? So x happens to live at address 100. Right? What value is stored in memory? Well, the value is actually -1. Right? So for primitive types, you store the actual value. On the next line, we have a variable t. So t appears somewhere in memory. Right? We're going to put this at address 101. Again, you can put it wherever you want. It can't overwrite an already existing variable. Right? So you can't put 2 things on one row. So we have a variable t. We're going to arbitrarily put it at address 101. Right? Now on the right-hand side, it says new array list. And so what's sitting in memory here is not the array list object itself. Rather, it's a reference to the array list object. The actual array list lives somewhere else in memory. Right? So here, I've stuck it at address 700. Right? I've labeled this box here with its type rather than a value. Right? Just so that we know that this happens to be an array list object. I don't know what's actually here. Right? So I have no idea how the array list class is implemented or what it looks like in memory, right? And I don't actually care. Right? All that I care is that the array list object is here at address 700. Right? You can kind of guess that there's probably an array that holds the elements of the list, but we don't know that for sure. Right? And so so what value does t store? Well, t stores the address of that object. Right? So when you see something on this memory diagram that has an A after it, that's indicating it's an address and not a numeric value. Right? So 700A means the address 700. Right? On the next line, we make another variable u, and we say u gets the value of t. Right? That's what the assignment operator means in most programming languages. Right? It means that thing gets the value of the thing on the right-hand side. Right? And so what are values in Java? Well, it's this column sitting out here in this third column. Right? So when you say u gets the value of t, then u literally gets the value of t. So the value of u is also 700A. What does that mean? U and t both point at the same array list object. And so it's like if you had a pointer in C and you made a copy of the pointer. Right? That also, you now have 2 pointers that point to the same object. Here we've got 2 references that refer to the same object. If you ask t to add an element to the list, right, it's that array list object whose size grows. Right? If you then ask u, how big is the list? Right? Well, u will also say that it's gotten 1 bigger because it also refers to that list. Right? So changes made to the object via t or u, the other variable can see those changes, right? Because it points to the same object after all. Right? And so that's the difference between a reference type and a primitive type. Right? Primitive types store the actual value. Reference types store a reference to an object. When you, I guess I should point out, when you use, when you use the variable t, right, it's slightly slower than using the variable x, right? Because using the variable x, all your computer has to do is go into memory beside the box labeled x and get the value, right? If you want to do something with t or u, right, your CPU has to do at least one extra step, right? It sees that the address here is 700, so now it has to jump into memory to find the object that it corresponds to. Right? And so there is this extra step or one level of indirection that has to be made when you use a reference type. The same thing happens in C when you use a pointer. Okay, so there are the fundamental terms. It's pretty important that you understand the fundamental terms and that you get them clear in your head. Otherwise, concepts that show up later on can be a little bit confusing. In particular, this difference between a reference and a primitive type, it's pretty important to get that straight. Otherwise, when you start to use objects and start to create your own objects and classes, you can run into unusual bugs, which are hard to understand unless you remember what a reference actually is. Okay, so now we start actually talking about object-oriented programming. So the people who study programming languages, and in particular object-oriented programming languages, like to refer to something called the object model. Right? And so this is a way of thinking about object-oriented programming languages in general. Right? So when your C courses, the C programming language is largely a procedural programming language. Right? So in the C programming language, you focus on breaking down programs into C source code files. In those source code files, you've got functions. Right? You pass information to the functions can operate on that information. They can return values back to you, or they can modify the information. In object-oriented programming, you break your program down in a different way. Right? So instead of breaking things down into functions, you break your program down into objects. The objects themselves, they contain data, and those objects can operate on their own data. Right? And so in other words, you can ask an object to do something and you don't have to pass it any extra information, or you don't necessarily have to pass it any extra information. Right? The information that it needs to operate on is already inside the object itself. And so there's four main elements of this model. So there's these terms here. I'm not going to talk about the fourth one right now. I'm just going to quickly tell you what these three terms are at a high level. We're not going to spend any time actually studying them in any great detail. Okay, so part one of the model is this thing called abstraction, right? And so you can read that quote there. Basically, the idea behind abstraction is that as a programmer, you generally don't care, or you don't want to care about the details of how something works, right? So for example, when you're using an int in C or Java, it doesn't matter, right? You don't care how the computer is adding the numbers, right? You don't care how the int is represented in memory, right? There's a whole bunch of stuff you don't care about. You just care that it's an integer and you can do stuff with it. Right? So the same thing is true in object-oriented programming. Right? You want to ignore everything that you don't care about at this particular moment, right? And you only want to focus on the stuff that is important right now. Right? So in your data structures course, you should have been told that there's this thing called an abstract data type. Right? So notice the word abstract again. Right? So an abstract data type is something like a list. So a list, what can you do with a list? Well, you can add stuff to a list. You can remove stuff from a list, right? You can use an index maybe to get something from a list, right? And then you are told, how do you implement a list? Well, you can use an array to implement a list, or you can use a linked list or a linked sequence of nodes to implement a list, right? And so there's many different ways that you can actually implement the list, right? The abstract data type is this thing called list, right? So you know the operations that you can perform with a list, but you don't know how it performs those operations. Right? And so that's the idea in abstraction, right? So I don't care if I have a list, right? I don't care how the list is implemented, right? I just care that you have a list. Right? Now in C, you don't really have that flexibility, right? So in C, you implement a list, you pretty much know, if you implement a list, you either get a linked list or a an array-based list, right? And you know it's a linked list or an array-based list, right? There's not really any way to avoid knowing that that is what it is, right? If you write a function that takes in a list, then it takes in either a linked list or an array-based list, right? But it can't take in either one and still work. In these object-oriented programming languages, abstraction lets you, abstraction leads to something called substitutability, right? So in other words, I can say a list has these operations, right? Add, get, set, size, and things like that, right? But you don't care how they're implemented, right? And so that lets you substitute different list implementations you write a method that accepts any kind of list, right? And it doesn't care how that list is implemented, right? So for example, in the collections class, there's this method binary search, right? That performs binary search on a list, right? What kind of list? It doesn't matter. It can be an array list, it can be a linked list, or some other kind of list, right? It works. Why does it work? Because of abstraction, right? Whoever wrote this method is basically telling you, hey, look, I don't care what kind of list this is. You can give me any kind of list you want, right? And this method will still work. Why can that work? Because the list, in this case, it's an interface, right? Says what methods all lists must provide, right? So whoever wrote binary search can write that method using whatever methods, can implement binary search, using whatever methods the list interface has. Right? They don't actually care how that list gets an element or sets an element. And so that's the idea behind abstraction. This idea exists, in all programming languages, right? Even C, right? But in the object-oriented programming languages, it leads to being able to substitute different types as needed. Okay, encapsulation also exists in most programming languages. So the idea in encapsulation is that you can compartmentalize the elements of an abstraction that constitute its structure and behavior. So what they're saying here is that every abstraction has data, right? And it has some sort of set of operations that you can perform, right? In encapsulation, you take the data and the behavior and you put it into one place, right? And ideally, you hide the data behind the behavior. Right? And so in Java, what ends up happening is the obvious place where encapsulation occurs is you make a class, right? That class can have data in it, right? So the class can have variables, right? And the class has a bunch of methods that operate on the variables. Right? So encapsulation serves to separate the methods, so the contractual interface, right? The methods of a type and its implementation. Right? So you can see what the methods are, but you can't necessarily see how the methods are implemented or what information they are operating on. Right? And so this leads to the idea of information hiding. Finally, there's this thing called modularity. So modularity just means breaking down a program into parts. That's all it means. Right? How do you do this exactly? It turns out there's many different ways you can do this. Java has at least 3 main mechanisms for implementing modularity. And so modularity is the idea that you organize your program into individual components, right? And then you place these components in certain places. So in Java, you can break your program down into classes, right? You can put your classes, you can organize your classes into packages. So we saw packages in the first lab, right? And then there's yet another level of modularity in Java, the thing called a module that we don't talk about in this course. All right, so how do these things look like in an actual Java program, right? So it's useful to look at what does an actual Java program look like. So your actual Java program is typically split into 1 or more files, right? So if you have a small Java program, it's 1 file, right? If you have a big Java program, it's thousands or tens of thousands or hundreds of thousands of files. It's also similar to C, right? Small C program you can put into 1 C source code file. If you've got a bunch of types that you defined yourself, then they go into their own C source code files. Well, ideally, they go into their own C source code files, right? But there are 1 or more files in a typical Java program. at the top of each file, there will be one or more package names. Right? So in our labs, everything's been in a package so far, I think. Right? So package lab 1, for example. Right? So the package mechanism is one of the mechanisms that Java uses for modularity. Right? It lets you organize your classes into separate packages. If your class needs the capabilities of some other type, right, then you may have to import that other type. In particular, you have to import the other type if it lives in a different package. So up here, you might have 0 or more import statements. Right? And then in the simplest type of Java file, there's one class. Right? Inside that class are the variables that are part of your class. Right? And so Java, these are called fields. Right? So these are or class variables. Finally, you can have, sorry, not finally. Every class is allowed to have 0 or more constructors. So we haven't seen these yet. We haven't implemented these yet. You've used them. So when you write new array list or new string, you're calling a constructor. Right? Where do those constructors live? They live inside the class. Right? And finally, your class can have 0 or more methods. So whenever you call a method, where do those methods live? Well, they're also defined inside of a class. And so there's a picture. So the details here don't matter. So if you can't read it, that's fine. Right? This is just trying to show you a picture of what a typical class looks like. Right? So at the top, you've got a package declaration. That's followed by 0 or more import statements. Right? Then that's typically followed by your class. And inside your class, there are fields, constructors, and methods.